The final thing I want us to look at from section 3-4, even though I've already given the homework from section 2, final thing I want us to look at is something called the second derivative test. And what the second derivative test is, it allows us to use the second derivative of a function to determine whether or not a value is a relative maximum, a relative minimum, or neither one of these. So let's look at something here real quick. I've got three critical numbers on this graph. Now we'll put it to work in a problem in just a second, but I've got three critical numbers in this point. Again, critical numbers, you do not have to change from increasing to decreasing, you just have to have a slope of 0. So I've got 3 points right here where I have a critical number. This first point right here, I've got a critical number. But if you notice that this critical number exists on an interval where I'm concave down. So if you have a critical number and it exists in an interval where you're concave down, then that point will be a relative maximum. Now, this point right here, this is a critical number, slope of 0 again, and you have a interval where you're concave up. So this happens to be a relative minimum. So what you do is you determine, okay, what's my critical number and what kind of an interval am I in? Now, this last one is neither a relative maximum nor a relative minimum. This happens to be a critical number, but it's also a point of inflection. We go from concave up to concave down. So it's not in an interval where it would be concave up or concave down. So we do not have enough information to determine, in this case on this graph, it would be neither of those. So the second derivative test reads as follows. A function f is a function such that f prime of c is 0, and the second derivative on that interval exists at point C. If the second derivative at C is positive, then C has a relative minimum. It's not a relative minimum because f of C would be the relative minimum. And if the second derivative is negative and f has a relative maximum, then you have a relative maximum at that point. If the second derivative is also equal to 0, then the test fails. You may have a relative minimum, you may have a relative maximum, or you may have neither. So in that case, to see if it's a relative minimum or relative maximum, you would want to go back and check with the first derivative to see if you're increasing or decreasing on those sides. Now, let's look at one of these real quick. Let's go with f of x equals, I'm going to pick one that's going to work neat, x cubed minus 5x squared plus 7x. Okay, so the first derivative here is 3x squared minus 10x plus 7. All right, so where does this equal to 0? This equals to 0. Okay, we've got 3x minus 7 and 3, or x minus 1. So again, checking that, that's negative 3x with negative 7x, which gives you negative 10x. So we got critical numbers at x equals 7/3 and x equals 1. All right, now let's go to the second derivative. The second derivative is 6x minus 10. So we want to know what the second derivative is at 7/3. So that would be 6 times 7/3 minus 10. which would be 14 minus 10, which would be 4. So here my derivative is 0, my second derivative is positive. So if I have a critical number where my second derivative is positive, then I have a relative minimum. And again, to figure out exactly what that relative minimum is, I would plug the 7/3 back into the original equation. All right, now let's figure out what the second derivative at 1 is. That would be 6 times 1 minus 10, which would be negative 4. So this would be a relative maximum, again, because it's a critical number, but it has a second derivative that's negative. So it's on an interval that's concave down, which is what we would have right there. So that's called the second derivative test. The second derivative test, even though second derivatives tell us about concavity, in this case, the second derivative test tells us specifically about extrema.